Up until this chapter, we've moved in straight lines. Now, for the first time, we're going to move in an arc along a curved path. The radius of this path is generally given, let's call it r. For the displacement, we're not going to say x because it's not horizontal, nor y because it's not truly vertical. We're going to say s. S is arc length, and you can think of s as standing for circumference. I know, C was already taken, but let's go with it. If we continue along in this arc in a full 360 degrees, we'll have done one cycle, one rotation, one period. How far will we have traveled in terms of distance? Well, we'll have traveled one circumference. What if we only go half that way? That would be a 180-degree turn, or half a circle, or half a circumference. If we go here, that's a quarter turn, that's 90 degrees. That's a quarter of the circumference. One way or another, if we're traveling in a curved path, then our arc length is going to be some fraction of our circumference. And all of the physics and math of circles comes from there. What fraction do we want of our circumference? Well, half a circle is 180 degrees. That's 360 times a half. A quarter of a circle is a quarter of 360. So we could continue measuring our angles in degrees and doing fractions of 360, or we could come up with a better system. I don't know about you, but I am not thrilled about having to do fractions of 360 degrees in every calculation for the rest of the next unit. Why are there 360 degrees in a circle? Who died and made 360 king? Turns out there are 360 degrees in a circle because the great god Zoroaster said so. Ahura Mazda, that's him. You know what he believed in? Monotheism. That's good. You know what else he believed in? Human sacrifice. That's bad. Well, the number 60 is sacred to the great god Zoroaster, so the Babylonian magicians, aka magi, aka mathematicians, who developed our current counting system, decided that all good things must come in 60s. That's why there are 60 seconds in a minute and 60 minutes in an hour. The circle is the most perfect of all geometric forms, so the Babylonian mathematicians decided that the only thing better than a 60 was 6 60s, the most perfect of the perfect, and that's why, to please the great god Zoroaster, we have 360 degrees in a circle. Well, this is the 21st century. None of us believe in Ahura Mazda, Zoroaster, Zarathustra, or the human sacrifice to keep the sun going that went with it, and I don't see that we need 360 degrees in a circle to please the great god Zoroaster. And I say, if we're going to deal with numbers, let's at least invent some numbers we can deal with. We already have a real pain coming in the circumference, which is going to be 2 pi r. And with some fraction of theta over 360, it's going to be nasty. All right. I say we invent a new system, a system designed for one and only one purpose. Knocking out that 2 pi and giving us a nice, tidy little formula that we can do in our heads without having to reach for a calculator 2,000 years before calculators were invented. And I think if we invent it, it's going to catch on. I'm going to invent the radian. And I'm going to use this piece of string to do it. A radian is defined in units of radius. I'm going to measure out 1 radius here. It's this much string. And I'm going to go around my circle. There! See the point on the circle where 1 radius translates into 1 arc length? That is going to be my first unit of angle. And the fact that it was formerly known as about 57 point something or other degrees doesn't faze me, and the Greek god Zoroaster can take 57 degrees back where he came from. That's 1 radian. Why? Because when I get all the way around a circle, I'll have 2 pi radii. That is 2 pi radians worth of circumference. Therefore, there are 2 pi radians in 1 circle, or 1 revolution, and that means our fraction is going to be a fraction out of 2 pi. And that's just gorgeous, because this is going to cancel out with this and give us S equals theta r. The only thing you need to know for angular motion, assuming that you have been working the whole time in the radian system, where 2 pi radians is 1 revolution. All you need to know is the angle and the radius, multiply them together, that's how many meters you've gone. Now let's take time into account. Divide by delta t, divide by delta t. Ask yourself, at what rate is this happening? S is length. It's measured in meters, and that gives us meters per second. Theta is angle. It's measured in radians, and that gives us radians per second. And that gives us a very nice little setup, because meters per second is clearly measuring velocity. Good old-fashioned linear velocity that we learned about all of first semester. And radians per second, change in angle or change in time, aka number of revolutions per second, or possibly RPM, revolutions per minute. That there is omega, angular velocity, revolutions per minute, radians per second, aka how fast you're spinning. And what's left is R. Please note the units on these pupsters, because they are not the units that meet the naked eye. This is meters per second as ever was. This is radians per second as ever will be. And that means this R here is not measured in meters. It is a conversion factor of meters per radian. Not meters, but meters per radian. You know what R is? R is my faithful piece of string. Remember, I measured out 1 radius. That's meters per radian, string, graph, and all. The same trick can be repeated. At what rate is your velocity changing? We call that acceleration. At what rate is your spin, your angular velocity changing? Well, we're going to call that angular acceleration. And we'll find that tangential acceleration, how fast you're speeding up or slowing down, aka, you know, centripetal acceleration? Not that one, is equal to your angular acceleration. Are you spinning faster? Are you spinning slower? Times the same conversion factor of R, meters per radian. Now, physics is still physics, whether you're spinning or not. Last term, we looked at linear acceleration. There it was constant, and all of these equations followed. Now, if we start with angular acceleration being constant, as a change in how fast you're spinning over time, the exact same physics will give us the exact same set of equations for spinning instead of for traveling. Write them out. Want to know how fast you're spinning in the end? Final angular velocity. You'll need to know your initial angular velocity, how fast you're spinning, your angular acceleration, speeding up, slowing down, or not at all, and how long you've been spinning and speeding for. The same conversion factor you have above will tell you how many revolutions or cycles you've made. We call that theta. We count it up in units of 2 pi radians. If you want to know how fast you've gone and turn it into how far, take your initial velocity, how fast you're spinning, angular velocity. Don't forget the t, and add an additional term of 1/2 alpha t squared to cover your acceleration, that you're not necessarily spinning at the same rate. Similarly, our last equation that came from conservation of energy, 1/2 mvf squared equals 1/2 mvi squared plus mgh. Cancel out the m's, and remember that the g was the gravitational field. We're not necessarily going down. We will get final velocity squared equals initial velocity squared, angular velocity this time, plus our additional term for the acceleration, same as before. Check it out, write it down, sort them, put a box around them. Your original formulas from the laws of motion, your conversion formulas, and your new angular kinematics formulas. Exactly the same as your previous chapter, same problems, same equations, same styles of solutions, different units. This is a part of a matched set with every other law of physics that we've seen works just as well when you're spinning as when you're traveling straight. We've seen rotational kinetic energy, which depends on how hard you are to spin and how fast you're spinning, thanks to a nice conversion factor. Also depending on R, we have angular momentum. Again, depends on how hard you are to spin. And vector direction here, how fast you're spinning. And we have, again, thanks to a conversion factor based on R, we have Newton's second law for rotation. What changes your momentum? A force. What changes your angular momentum? A torque. That torque depends on how hard you are to spin, plus how fast you want to increase or decrease that angular speed. And when you've succeeded in doing that, you'll be able to change your angular momentum given enough time. Again, new set of equations, box them, ready to use in the same types of problems.